Welcome back to Physics with Miyoshi. Today we're going to talk a little bit about fluids, a little bit more about fluids, but now we're going to talk about them in motion. A couple of things we need to look at is, first of all, there's steady versus unsteady motion, and when we have fluid flowing in a, whether it's a pipe or a blood vessel or a stream, probably you've noticed, if you've stood by a stream, you've seen that there's, if you have water going through the stream on the outside of the stream, it goes slower than in the middle, and it'd be the same. That would be an example of more or less unsteady. If it was steady, then all these guys, every particle of water or whatever the fluid was, it would be going the same speed. In something more like a blood vessel or in our stream that we've seen, we can see that even as I change things a little bit, maybe I have little protrusions out there like that. Then we can even get what's called turbulent flow, where you might even have a particle that changes direction, or some that go the opposite direction, and so forth. So those are different types of flow. We also have incompressible versus compressible versus incompressible fluids. Compressible, usually that has to do, we would consider lots of times, that's a gas. It changes its volume if we put pressure on it. Where an incompressible fluid would be something like a liquid, where mostly it does not change its volume, even if its pressure changes. We also have something like viscous versus non-viscous fluid, and viscous fluid would be something like honey perhaps, or oil. It doesn't flow really well because the layers, if you will, of fluid, the outside layer is going to go slower, and as it touches the inside layers, it causes them to go slower as well. That would be a viscous fluid. A non-viscous fluid would be where they would tend to be more steady stream, where everything has the same flow rate. And then we have the ideal, of course, which is an incompressible and non-viscous fluid. In an ideal situation, you can look at a stream, you can look at a flow pattern, you can see actually streamlines going along there, something like you would see in a wind tunnel or something like that. But these are kind of not idealizations, but they're kind of categories of different flow or different motion of fluids. They bring us to something called the equation of continuity. And the equation of continuity just says that if I have a single pipe, and let's get this pipe back here. If I have a single pipe that's got a steady flow rate, so all my particles, no matter where they are in the fluid, are going the same speed, and there's only one entrance and one exit, then I can say that the mass flow rate has got to be the same regardless of how big the pipe is. Whether it changes shapes or stays the same, the flow rate has got to stay the same. And this equation right here, it says as rho, or the density times the area times the speed of the particles, and in this case a steady flow rate, they're going to all be traveling at the same speed. At one point, it's got to be equal to the density times the area times the speed of the particles at any other location. And if I have something like this, where it's a large pipe in the one side and a small pipe on the other side, I could use this equation as long as it's the same density, which would be the same liquid flowing through there, or the same fluid flowing through there. As long as it's incompressible, it's an ideal fluid, then I can get rid of the rho, the density, and I can look at just the volume flow rate. And the volume flow rate is the area, the cross-sectional area of my pipe times my velocity times my speed has got to be equal to the cross-sectional area times the speed at any other location. And we can see, if you look at the units there, the cross-sectional area is meters squared, and then the velocity, or the speed, is meters per second, so this ends up to be meter cubed per second. And if I think about this volume here and this volume here, they've got to be the same. And the reason why it's going to be wider here is because the number of molecules that pass through here and the volume, it's got to be the same in any given instant here and here. So that's why if you ever played with the hose and you plug up the hose part way, you get a faster jet out the end than if you keep your thumb off of there and just let it flow normally. That's why you have a greater speed of a greater flow rate, volume flow rate. Well, the volume flow rate's got to stay the same, but the particles will actually change speed. And then we could show this with this equation. As the area gets smaller, like it is here, then the speed must increase, so I get the same amount of volume change. So, fluids, they do go in motion, and we have a few ideas to think about them. And we have this equation of continuity, talking about flow rates, and just a little precursor to Bernoulli's equation and doing a little bit more with fluids. So, hopefully you enjoyed talking a little bit more about fluids and fluids in motion, a little bit more interesting than fluids that are not in motion. And so hopefully tune back in to hear more about fluids. And thanks for tuning in with Physics with Miyoshi.